Good afternoon, everybody. Welcome to lecture. Today we're going to be talking about NMR spectroscopy again. We're going to focus on spin-spin splitting, which is this feature of NMR spectra that you can use to determine the connectivity of molecules. Really powerful stuff, very useful. First of all, though, I want to tell you about a molecule of the day. So this is something that we're doing 5 times before the next exam, before the first exam. We had one molecule of the day last week. We talked about cinnamaldehyde last time. Today, I'm going to introduce another molecule for you. This one's called cucumber aldehyde. That's its kind of common name. It has a systematic name. It is 2E6Z nona 26-diene-al. You don't need to be able to process the entirety of this name, but I thought it'd be useful to just bring it up because we talked about alkene naming last semester. So just as a brief explanation of what this name is all about, you start numbering at the carbonyl and then you go to the end of the molecule, and there's 9 carbons. That's how you get the nona part. The fact that there's 2 dienes leads to diene part, and this is telling you the double bonds are in the 2 and 6 positions here and here. And then the E and the Z tell you what the stereochemistry is. The 2 and 3 double bond is a trans type double bond, or E for entgegen. And then the 6-7 double bond is the Z type. We would also call that cis. So not that the systematic name is super important, but I just wanted to point it out. This is essence of cucumber. So I thought about this as I was harvesting cucumbers in my little tiny garden. We've gotten a lot of cucumbers. Good year for cucumbers in our little patch. So anyway, what makes them smell and taste distinctly like a cucumber is this molecule. You can notice some similarities to cinnamaldehyde. The whole right side of the molecule is exactly the same. So there are some themes that you're going to see in natural products chemistry and flavor and fragrance chemistry, which is a personal favorite of mine. I love how you can figure out what molecules are present in foods that make them smell and taste really good. I think that's pretty fun. And this one is that type. Now, 2 things I want to point out about this also are that the double bonds are not exactly the same. Other than being cis and trans, there's another difference. This one is what's called an isolated double bond, not conjugated. Or we would describe it as non-conjugated. Meaning there isn't another double bond next door where you can do this double bond, single bond, double bond pattern. The one over here on the right side of the molecule, though, it is. So it's part of a conjugated system that I'm gonna just lasso out here with a dotted line and say, this is an example of conjugation. And right now we're learning to just identify it by this pattern of double bond, single bond, double bond. Turns out that, and we're going to learn more about this as the semester goes on, but there's some special characteristics of a system like this, and the bonds don't behave as though they were isolated. They're conjugated, they're in communication with each other. But this is a conjugated C double bond O. Because of this double bond, single bond, double bond pattern, and that results in a lowering of its frequency. And we talked about this quite a bit when we're looking at IR spectra, and we'll see it over and over again, that when you have a carbonyl in this type of context where it's next to a double bond separated by a single bond, it gets lowered. So this conjugated C double bond O is much lower in frequency. It has a stretching absorbance in the IR spectrum at about 1685 inverse centimeters. So normally you'd expect to see an aldehyde carbonyl, if it wasn't conjugated, more like 1710. So just another example of this kind of a phenomenon. And now you have 2 aldehydes in your molecules of the day, so you're not going to be able to just recognize aldehyde functional group to distinguish them. You'll just have to remember a little bit of something about the other parts of the structure. Cucumber aldehyde has a chain, and cinnamaldehyde had an aromatic ring. Maybe that helps. But that's a molecule of the day. Then the other thing that I want to do is talk about our survey question from the last time. So here's that survey question. It is asking how many unique types of protons and carbons are present in the molecule below. This molecule's got an aromatic ring. It has an amine group on it. There's NH2 here, and then there's an OCH3. And these are all the different options that you've got, and I'm going to put up the solution and then we'll talk about it. The correct answer was E, and the reason is that this molecule has an internal mirror plane of symmetry. You might not have observed it or recognized it with the OCH3 group shown the way it was up there. It looks hard to find the mirror plane of symmetry when, let me just scroll back up here. And it doesn't look like this methyl group is in a mirror plane, but if you rotate it, you can position it such that you can draw a mirror plane of symmetry through the molecule here. So in other words, the methyl group gets bisected by this mirror plane, and that means that these two H's are the same as each other, these two H's are the same as each other, and these NH2s are the same as each other, both because they're mirror images and also because they can rotate. So this molecule has got the methyl protons as one type. Remember, all the protons on any given methyl group are always the same by rotation. That's one type. The two H's here is another type. There's another type there, and then the NH2 type. So that's 1, 2, 3, 4 proton types. For carbon types, you can do a similar thing. You can count carbons. That's one unique kind of carbon. That's another type. So that's 1, 2, 3, 4, 5. So 4 types of protons, 5 types of carbons. And I have this diagrammed in the solution where I'm showing the protons with the lowercase letters and the carbons with the uppercase letters. So hopefully that makes sense, and hopefully you got the right answer. Let's check and see how the class did. Well, pretty good, but it looks like there was a lot more people responding D than I would have hoped. So take a look at your answer and see, if you selected D, why did you get 5 proton types? See if you can figure out, what was going wrong there, and why did you only select 4 carbon types? So think about that, and also too, A, B, C answers, sort that out too. But just look at these maybe a little closer. You can always build a model too, remember. The other thing about the aromatic ring that's important is that the double bonds aren't localized. So this molecule has got an internal mirror plane of symmetry because all the bonds, it's not like there's a single bond here, double bond here and a single bond there. They're all about a bond and a half. So there's a lot of symmetry in aromatic rings. Okay, any questions about that molecule of the day or the survey question? All right, well, let's talk about this concept of spin-spin splitting, which is a big one, and it's one we're gonna need to know about for lab this week. So most of you are in the lab course. This week, we're gonna really dive into spectra interpretation, and the whole lab is about getting practice interpreting spectra, IR, mass spec, and NMR, both proton and carbon NMR, when you have them to identify an unknown. And that's going to require understanding of this spin-spin splitting concept. So I sent everybody that's in lab an email message with an attachment that's got a bunch of spectra on it. We're going to write on those in the lab tomorrow and try to figure out what those unknowns are, B through H. So come to lab and work on those, and it'll be a good experience getting started interpreting lots of the spectra. It's just one of those things you have to practice a lot to get good at. Nobody's good at it. Nobody's great at it right out of the gate. It's always slow. It's always awkward. But the more you do it, the better you get at it. All right. So spin-spin splitting. It is something that you see in many proton NMR spectra. And here's the origin of the phenomenon. When non-identical protons are near each other, and what I'm going to say to define near is I'm going to say within about 3 bonds, they split each other. And as an example, I'm going to show the compound that's listed in the textbook that introduces this concept. The molecule that is in the textbook is a 2-carbon molecule that's got one of the carbons having 2 bromines on it and 1 proton. And then the other carbon has 1 bromine on it and 2 protons. So the first thing that you need to do when you see a molecule is decide if the protons are the same or if they're different. So if we start from the left and work our way right, there's a proton over here. It's on a carbon that's attached to two bromines, and bromine is an electronegative element. So this H feels a pretty substantial pull of electron density away from it due to the two bromines. To a lesser extent, it feels the pull of this bromine on the adjacent carbon, but it's not as strong because these inductive effects are really localized. They make the biggest impact when they're close, and these two bromines are very close. Then there are two H's over here, which I'll draw squares around just to indicate that they're different, because they're on a carbon that has only one bromine. So these H's are de-shielded by the bromine. They feel the effect of this one bromine fairly strongly, and these two bromines that are further away in a more muted way. Between these two, this H is more electron poor than these, so this H would appear more to the left, more in the downfield region. These would appear more towards the right side, a little further in the shielded part of the spectrum. But they're definitely not the same because they're different chemical environments. These two are the same because there's a mirror plane of symmetry that runs through the molecule. So you could see these two are reflections. Build a model of it to be sure, but that's the way that works. So you expect to get two signals for these, and you do. And I'm going to show you what this looks like on the screen. There's one signal here and one signal here. This signal at 5.6 or so is the signal for the CH. The other things that are attached here are the two bromines. This signal at 4.1 is the CH2 that has the one bromine on it. But if you look really carefully at them, they're split into multiple peaks. That's what splitting is. This signal over here, when you blow it up, which is what this inset is trying to tell you, is that this, you look at it closely, it's actually three peaks. We call this a triplet. Three peaks is triplet. And the characteristic of the triplet is it's a small peak, big inner peak, small outer peak. So these three peaks in this ratio represents a triplet. That's a splitting phenomenon. This peak right here is actually split into a doublet. There's two peaks, and they have equal intensity. So this is our first example of spin-spin splitting. The reason that this happens is that the H's on these different carbons are communicating with each other. Remember how we said that protons are kind of like small bar magnets? They behave like bar magnets with a north pole and a south pole. Well, if you imagine putting two magnets near each other, like that's a magnet, and these two are magnets. When they get close, they influence each other. These H's have magnets that can either align with or against the applied magnetic field, the big magnet that we put the sample inside the spectrometer. Same thing with this one. This one proton can either be spin up, aligned with the magnetic field, or spin down. Those two possibilities lead to the two different peaks that you see in a doublet. So these H's appear as a doublet because they have one neighbor that has two possible spin states, an up and a down. Now, I'm not going to go into the details of exactly what kinds of spin states give what kinds of splitting patterns. It's something that the book goes into, and it's interesting, but we don't have time to really address it in a big way. But what I will tell you is that you got to figure out, when you look at a molecule like this, what you're going to expect to see for splitting. And the first thing you should do is ask yourself, how many neighbor protons does this signal have? Does this proton have? This proton over here has two neighbor protons. To count as a neighbor, it has to be different. It can't be the same type of proton. Identical protons don't split each other. We're going to talk about that as an important rule. But this one has two neighbors. And it turns out there's a rule that you can use to predict what it will be split into, and this is called the n+1 rule. We're going to talk about this too. So n+1, where n is the number of neighbor protons, tells you what the splitting will be. So this H gets split into 2 + 1 = 3. It gets split into 3 protons because it has two neighbors. Two neighbors, and then you add one, and you get 3 peaks, so you get a triplet. We go over here. These two H's are the same type of proton. They don't split each other, so you count them collectively. It's one type of proton that gives one signal, and that one signal is split by this one neighbor. So these collectively, what I'm going to say, I'll point to these and say, these have one neighbor. So they get split into n plus 1, and in this case, the n, neighbor, there's one of them, 1 plus 1 equal 2. They get split into a doublet. So their signal is split into a doublet because of this one neighbor. And that's how it works. We're going to look now at a bunch of different examples of this, and I'm going to put down some splitting rules that are going to help you pretty much summarize all the stuff I talked about like identical protons not splitting, the n plus 1 rule, ratios of peaks, all that stuff I'm going to put down in a series of like rules on the board here. But do you have any questions about this particular example? Like, why is it that you see this splitting phenomenon? Triplet for the one that has two neighbors, and then doublet because of the one neighbor. The thing you have to be careful of is it isn't the number of protons, it's how many neighbors it has. So this is one proton, but it has two neighbors, so that's a triplet. That's two protons, it just happens to be a doublet, that's a coincidence. But it's a doublet because it has one neighbor. The splitting tells you what is nearby. It tells you what neighbors are present. It's the neighbors that give the splitting. When you see one proton, this would have an integration value of 1 that's split into a triplet. It's telling you, I am one proton and I have two neighbors. That's what it's trying to tell you. Over here, if you looked at the spectrum and you looked at the integration for the signal, it'd be integration value 2. So that tells you there are two H's, and the fact that it's a doublet tells you it has one neighbor. So the spectrum is trying to tell you how many protons you have and then what kinds of neighbors are present. And that's what we're going to get practice unraveling here. So some rules for splitting, first of all. These are good things to think about. First rule of splitting is that identical protons don't split each other. Identical protons don't split each other. So if you have a CH3, there are 3 protons there, but they're all the same type, so they don't split each other. Only unique protons function as neighbors for purposes of splitting. The next rule is this n plus 1 rule. So n, where n is a number, neighbor protons split a signal into n plus 1 peaks. So that's what we were talking about before with if you have one neighbor, add 1, you're split into 2 peaks. If you have 2 neighbors, you're split into 2 plus 1, 3 peaks, and so forth. So count the neighbors, add 1, and that's how many peaks you expect to see for that signal. Third rule is that to split each other, protons need to be nearby. And maybe what I'll say is to count as a neighbor. For splitting, protons have to be nearby. Need to be, and I'm going to define it quantitatively. I'm going to say within 3 bonds. Sometimes 4-bond coupling is observed. I'll just say is possible, but it's not common. Not nearly as common. So we'll talk about examples of mostly 3-bond coupling. 2-bond coupling is also possible, but the 2 protons have to be different, so that's a kind of another rare situation, less common. We're going to focus on the 3-bond coupling for now because it's by far the most common one you're going to run across. And let's just go over here and take a look at this molecule just to go over what I mean by 3-bond coupling, the H's have to be within 3 bonds of each other. And if you look at this H and these H's and count the bonds that intervene between them, there's a CH bond here, that's 1 bond. There's a CC bond here, that's 2 bonds. And then there's a CH bond here, that's 3. So 1, 2, 3 bonds. These are close enough to count as neighbors and split each other. If they're 4 bonds away, I would say for right now, unless there's some special situation, just consider it to not be able to couple. That won't split because it's too far away. So 4 bonds, no. 3 bonds, yes. All right, next thing we're going to talk about is the ratios that you observe with splitting. So rule number 4 is just going to specify what the split signals look like. In the n+1 rule, you get certain patterns. So I'll say n+1 rule peak ratios follow something called Pascal's rule. Pascal's rule is a cool sort of thing that this mathematician Pascal figured out a long time ago. It's can be recreated really easily using this geometric kind of pattern where you build a pyramid with numbers. I'm going to show you how to build a pyramid. So start with a 1 on the top of the pyramid. Okay. Then we're going to build another level of the pyramid, putting a number out to the left of it and a number out to the right of it, and it's going to be a 1. So I'll put a 1 over here. Oh. Need better chalk, stronger chalk. There you go. All right, now we're going to build the pyramid another level down, and we're going to put 1s on the outside again. So on the left side of this 1, I'm going to put another 1. And then in the middle here, in this space between these two, I'm going to add the sum of these two numbers. So 1 plus 1 is equal to 2. And then on the outside of the pyramid, on the right side, I'm going to put a 1. And this is going to be the pattern throughout now, is that the outsides of the pyramid, when we build the outer side, it's always going to be a 1. And then the inner numbers are going to be sums of the ones that are above it. So if we build another level to this, on the far left side, there's going to be a 1. And then 1 plus 2 is equal to 3. 2 plus 1 is equal to 3. And then a 1 on the outside. Let's build it another level down. 1 here, 4, 6, 4, 1. Build it another level down. We'll just kind of keep going for now. 1, 5, 10, 10, 5, 1. And I'm going to go one more level down because these are some of the most common splitting patterns that you see. And we're going to see one of these tomorrow that's at the bottom in the lab. 1, 6, 15, 20, 15, 6, 1. So what we've done with these is to build a pyramid that shows the relative ratios of the areas of the peaks in any one of these split signals. So a singlet is obviously just one peak. All the area is under the one peak. But when you have a doublet, 2 peaks, the area is split 50-50 between them. So the peaks have equal intensity, 1-to-1 ratio of areas under a doublet peak. When you get to, and maybe what I'll do is I'll draw a little tiny picture of this over here. Singlet. Doublet has 2 peaks of equal intensity. Doublet. When you have 3 peaks, a triplet, the area ratios are 1 to 2 to 1. Sketch a little cartoon of this, and I'll try to draw the inner peak as twice as tall as the outers. Triplet. As you go to 4 peaks, it goes 1 to 3 to 3 to 1. So that would be a small peak followed by a much bigger one, and then a smaller one. So this would be something called a quartet. And as you go down, you get the same kind of pattern where it just basically the areas mimic the ratios in Pascal's triangle. When you have 5, it's called a quintet. When you have 6, it's called a sextet. When you have 7, it's called a septet. But it's the number of peaks and then the areas of the peaks. And the other thing you'll notice is that these are all symmetrical about the middle point. So Pascal's triangle is symmetrical. In other words, the left and the right sides are mirror images. So it'll always be like that with n+1 splitting. So one thing to just be aware of is that, and I'll put this as rule number 5, not all splitting follows the n+1 rule. Most of the examples I will pick the splitting will be a type of splitting that follows the n+1 rule and gives multiplets that look like this. But once in a while, with real molecules especially, what you're going to get is sometimes complex splitting. So I'm going to say complex splitting can occur, and if splitting doesn't follow the n+1 rule, don't try to make it fit. Don't try to interpret the splitting, because you'll get confused. Essentially, when you know you can interpret n+1 splitting is when you see a multiplet or a split signal that follows this Pascal's rule pattern. A multiplet that's symmetrical and it has peaks that follow these patterns. So we're going to see examples later, probably later today, and also in the lab, where the splitting just gets complicated and the rules for that are more difficult to describe, and it's really kind of beyond the scope of this class. What we're going to do here is we're going to kind of give an essential introduction to NMR spectroscopy interpretation. We're going to learn enough so that you can get really a large amount of information out of the proton NMR spectrum, but we're not going to learn it all because we simply don't have time. I teach an upper level class where we spend the majority of the semester just talking about NMR. So it's a concept that's really, really wide and deep. And it's a very powerful technique, but we don't need all of that for this course. We're just going to focus on the essential stuff, the n+1 rule type splittings. So I'll point out when we get a spectrum that doesn't follow it, I'll point that out and say, for this signal that's split with complex splitting, you can still get the chemical shift information. You can still get the integration information. It's just the splitting isn't going to be useful. The complicated splitting that you see won't help you. But, it shouldn't confuse you, though. So that's my goal. All right, more rules. One more rule, and that's that sometimes, most of the time, NHs and OHs don't actually split each other. So this is the last rule, and then we'll get into interpretation of spectra. So what are we on now? Rule number 6. NH and OH protons do not split. They're neighbors. And appear as singlets. So for purposes of splitting, NHs And OHs just don't do it. Even if they're close enough, even if they're within 3 bonds, usually they don't engage in splitting. They just don't communicate with their neighbors the same way other protons do. The reason is that these are strongly hydrogen bonding, and that leads to a phenomenon called rapid proton exchange, where the NHs and the OHs in a molecule get traded really, really fast on the NMR timescale. They're flipping molecules really quickly, and that leads to them not appearing to be neighbors, because one NH proton doesn't sit in one spot long enough to really be counted as a neighbor, is a way to think about it. So basically, just make sure you're not confused by that. OHs and NHs usually don't split each other. For purposes of this class, that'll always be true. In reality, there are some cases where NHs and OHs will split their neighbors and they will appear as split signals, but we're not going to look at any examples like that. So NH and OH protons for this class don't split their neighbors and appear as singlets. Okay, let's see here. Put this down. Just do this. Okay. Let's look at a molecule, draw a molecule, and predict what we would expect to see for its spectrum. Any questions about these splitting rules, though, first of all? Okay. You'll probably forget some of these as you're going through, and you'll be like, oh yeah, that's right, I remember that now that you mention it. So that's one of the points of like studying, and our practice tomorrow in this workshop type experiment is going to be focused on just getting a mastery of all the rules all at once. Let's take a look at a molecule like this. Some of the questions in the homework are going to ask you to predict the spectrum of NMR spectrum of an organic molecule. This is the molecule ethyl acetate. And let's first of all start from the beginning. How many unique proton signals would you expect? How many unique types of protons are there in the molecule, do you think? 3. I see some votes for 3. Awesome. Yeah. There are the CH3s on the left side. I'll call those A. There's a CH3 on the right side. Those are always the same as each other. The H's on any one CH3 are always the same as each other. But that CH3 and that CH3 aren't the same, because this one's attached to a C double bond O, and this one's attached to a C that's attached to an O. So different chemical environments, they give different signals. And then the CH2, that's different than any of the other protons because it's a CH2. It's on a carbon attached to a very electronegative oxygen atom, so that makes it unique. I'll label those as C, referring to the H's here. And they are the same as each other because there's a mirror plane of symmetry in the molecule that makes these two H's reflections. And if you build a model, you can arrange it in its most symmetrical conformation, and you'll see that there's a way to bisect it right down the middle. And those two are reflections. Okay, so we're going to see 3 signals. Let's predict, based on chemical shifts, about where they will be. And this is going to require that you'd get your table out and you'd look to see protons in what kind of chemical environment are we looking at here. So when you've got protons on a carbon that's next to a double bond, like a C double bond O, that produces a particular kind of chemical shift. For methyl groups, it's usually about 2.1 parts per million. If it were a CH2, it would be more like 2.5, but that's the region you're going to expect to see it. You're going to look, that's where it will be about. The C signal here, CH2, these are H's that are attached to a very electronegative O. You look at the table, you look at that entry, and it's going to say 2.5 to 4.0 parts per million. And these are going to be at the high end of that because oxygen's really electronegative. And I believe the spot where you actually see it is 4.1 parts per million. So if this was a predict the spectrum kind of problem, you're not going to know exactly 4.1, but what you'll know is the ordering of the chemical shifts in the approximate region. Then there are these CH3s. Now, if this was an isolated CH3 that wasn't near any electronegative or deshielding group, it would be 0.9. But since it's one carbon removed from an O, it's deshielded a little bit by that. Not a lot, because it's not directly attached to it, but this one shows up at 1.3 parts per million. Okay, so we got our three signals. We've got the position on the spectrum where we're expecting them. Now integrations. How many H's are there going to be? All you have to do is count them. There are three H's here, so we're going to get a signal that's going to have relative area 3. These have area of 2, so I'm going to say 2 H's here. And then there are 3 of this type, so there's 3 H's here. So our signals are going to be in a 3 to 2 to 3 ratio. That's what we'll see for areas. The size of the peaks, the areas under the peaks are going to be like that. And then finally, there's the splitting. What are we going to see for splitting? This is the new thing. So if you go over here, what about that CH3? Are there any H's that are within 3 bonds? No, there are not. And if it's helpful, you can draw out the H's. But remember, there's a CH bond here. So there's one bond between the H and the carbon. There's a bond between this carbon and that carbon. That's 2. There's a bond between carbon and oxygen. That's 3. There's a bond between oxygen and carbon. That's 4. And then there's a bond between carbon and hydrogen. That's 5. That's way too far away. So these H's are isolated in a part of the molecule where they can't communicate with any other protons, and they show up as a singlet. No neighbors. So you would see a singlet around 2.1, 3 H's tall. Big, I mean area, not tall necessarily. How about over here? Our signal C. There are 2 H's. How many neighbors do these H's have? There are 3 over here. It's one kind of proton, but you count all 3. If there's 3 of them, count 3. So this signal has 3 neighbors. So it's going to be split into 3 plus 1, 4 peaks. So this is going to show up as a quartet. 3 neighbors, add 1. That gives you the 4 peak splitting. Signal B is a CH3 that has 2 neighbors. So 2 plus 1 is 3. This is going to show up as a triplet. So if I go over here and draw a spectrum for this thing, a predicted spectrum, I'm going to have my 0 mark right there. I'm going to put 1, 2, 3, 4, 5, 6. We're not going to use this part of the spectrum. The spectrum usually gets printed from 0 to 10. But if there aren't any peaks of interest in the far left side, it probably zooms in on the part of the spectrum where the peaks are so you can see them more clearly. So I'm just going to zoom in on this part of the spectrum right now. I'm not going to bother to draw 8, 9, and 10 because there's no peaks over there of interest. So let's look at our A signal. Our A signal is a triplet at about 2.1. So we're going to have a triplet. This is due to the A protons. Then we're going to have a quartet at 4.1. So we look at 4.1, there's 4.1. We're going to have a quartet. Should make that a little bit smaller. I'll call that one C. And then we've got, oh, sorry. Why did I do that? A is supposed to be a singlet. All right, A is supposed to be a singlet. All right, let's make a singlet out of that. 2.1, we got a singlet. Quartet at 4.1, and then there's a triplet at 1.3. So something like that is what we're going to see. And there would be integration indicators here too. You would see probably integral traces over these signals to indicate the relative number of protons. So the integral traces might look something like this, where you get trace there and trace here. You see these are like the same height from the bottom to the top because they each represent 3 protons. This one is signal C. It only represents 2 protons, so its integral trace is only going to be like 2/3 the height. So if you got your ruler out and you measured the heights of these traces and figured out the ratio based on the heights of the traces, that would give you the relative number of H's. it would be a 2H to 3H to 3H ratio. So that's in the forward direction. That's like if you've got a molecule predicting its spectrum. More often, probably than not, you're going to have a spectrum and you're going to have to decode what molecule it came from. That's the usual way that these problems work. But you just work the process in reverse. You look at the signal and you ask yourself, what's the integration, what's the chemical shift, what's the splitting, and then try to figure back what it was. So to get some practice with this, I've got some examples that I want to go through. And we'll go through them kind of slow, and we'll look at them, and then in lab tomorrow, it's just more of the same. A lot of interpreting spectra. So I'm going to get out a different recording for this, because I want to use my iPad for this. This is an NMR spectrum, and what you want to do is look at it and see, what are we looking at here anyway? We can tell it's a proton NMR spectrum because there's a label on the bottom. It goes 0 to 3 parts per million. The scale usually goes to 10, but we're not seeing any peaks in this, so we're just focusing on the region where we're seeing peaks. So that's okay. And we can see the other thing that's here is we've got the part per million chemical shift down here. There's tetramethylsilane that's shown here. I think what I'll do is just do this. Tetramethylsilane is just the internal standard that was added to enable us to mark the 0 position. So just don't confuse that for part of this molecule. Then we've got signals at about 2 parts per million, about 1.4 parts per million, 1.1 parts per million, and then like about 0.8 parts per million or so. And some of these are split signals, so it's giving us insets of that. The one at 1.4 is clearly a quartet. It's shown over here on the left side in its own box. And you can tell it's a quartet because it's got 4 peaks in a 1 to 3 to 3 to 1 ratio. Then at the 0.8 or so part per million region, there's a triplet. And you can tell it's a triplet because there's 3 peaks. They're in a 1 to 3 to 1 ratio. And then we've got a singlet at just about 1.9 or so, and a singlet at 1.1, which is 6. All right, so the integrations are nicely worked out for us. Let's maybe make a list of what might be going on here. So the quartet is the 2 H's. And how many neighbors does that have? Okay, so we've got to work with the n+1 rule here. If it's 4 peaks, there must have been 3 neighbors that made it. So I'm going to put a note here, and this is what I would recommend doing. I'm going to say 3 neighbors. So it's 2 protons that have 3 neighbors. 3 neighbors is like a methyl group probably. So probably what you're looking at is this signal right here is probably 2 H's, maybe a CH2 that has 3 neighbors. All right, let's go take a look at the other split signal, the one at 0.8. This one is a triplet, which means it must have 2 neighbors. And it's got 3 H's. So it's 3 H's that have 2 neighbors. So these are related, these splitting phenomenons. The 3 H's that have 2 neighbors, let's just maybe put this on here. I'll put the labels down here for, I'll label this one as A. I'll label this other signal as B. Label that one as C, and this one as D. So we have these 4 different signals. The signal A is just some kind of isolated H. We don't know what it is exactly, except that there's a hint in the upper left-hand corner. It's really subtle, but it says it's an alcohol with formula C5H12O. You'd probably get that information from an IR spectrum. You'd see a big, bold OH signal in the IR spectrum around 3500. It'd be broad, it'd be smooth. So OH. And we know that OHs aren't split by their neighbors. They don't split their neighbors. So we're looking for a singlet to assign to the OH. There's two singlets in this molecule. One of them is for 6 hydrogens, and that doesn't really make sense because an alcohol has just one H. So this signal A, I'm going to assign it as probably being an OH signal. That's got to be most likely our OH. Okay, and then the B and the D are the split signals. Let's look at C first of all, because I think C is maybe a little easier to get. C. There are 6 protons here that are all the same, all exactly the same. How could you get 6 identical protons in a molecule, do you think? Just looking for ideas. Yeah, I mean, they could be in some sort of molecule that's got a chain. And usually what I do when I see integrations, I think multiples, like this 6 is a common multiple of 3. So there's 3, 6, 9. That's the way identical methyl groups come. So 6 protons might indicate 2 identical methyl groups. So I'm going to say, as at least a, kind of a working hypothesis, that signal C is 2 identical methyl groups, a CH3. And what I'm drawing here is a bond to the CH3, and the squiggle that I'm drawing is just saying, I know it's attached to something, but I don't know what. And then there's got to be another one that's exactly like it so that its signals are the same. So signal C is probably some 2 methyl groups that are exactly the same. Maybe because they're, they've got some symmetry that makes them the same. All right. Let's look at this, this B and D pattern. So B and D are this collection of 2 signals, 2 H's here that have 3 neighbors. So that's like a CH2 that's next to a CH3. That's what that's telling me. So signal B, it is a CH2 because it's got 2 H's. I'm going to draw that a little better. So that's the B signal right there. But the neighbors, the splitting is telling me there must be 3 protons next door. So on the next door carbon, there's 3 H's. So I'm going to say CH3. If we look at the D signal is related. It is a CH3 because there are it's integration 3. The D signal has 3 H's. It represents 3, but it's got 2 neighbors. So this is probably a CH3 that's next to a CH2. And so what you're seeing here is a really classic sort of pattern, and you'll see these as you go through and you look at NMR spectra, but classic pattern for an ethyl group, a CH2, CH3 that are next to each other. The pattern for ethyl is what you're seeing here, and you'll see this again, if you come to lab tomorrow and you work on these problems, you'll see this at least 2 more times tomorrow. There's a quartet, triplet, in a 2-to-3 ratio, 2 to 3. That's telling you CH2 adjacent to CH3. So the molecule has an ethyl group in it. And then we know that A signal that we were talking about, A is the OH group. So let's put this all together and see what we've got. We've identified a bunch of pieces, and this is kind of the way you'll want to do it when you're solving these spectra is get the pieces from the spectra, and then at the end, when you've got all the pieces figured out from the NMR spectrum and the IR spectrum and the mass spectrum, put it together and try to make a molecule out of it. But before we try to put it together, let's make sure we have all the pieces. Okay, so let's count atoms. We know that this molecule from the hint up at the top has 5 carbons, 8 hydrogens, so 12 hydrogens, 5 carbons, 12 hydrogens, and an oxygen. Let's make sure we've accounted for those with the pieces that we have. we have an OH right here. So that accounts for the oxygen and one of the hydrogens. Let's count up all the other hydrogens that we've got and just see how many we have. We've got the two identical methyl groups here and here. That's 6 hydrogens. So now we're up to 7 hydrogens. We've got a CH2. That's 8, 9 hydrogens. And then let's look at the CH3 here. That's 9. That's 10, 11, and 12. So essentially, when you add up all the hydrogens that we've identified in the proton NMR spectra, we've got them all. That means there's no hydrogens that are missing somewhere. They would all appear in the proton NMR spectrum. Let's add up carbons. We've got, and maybe what I'll do is I'll circle these in a different color. We've got a carbon here, and a carbon here, carbon here, and a carbon there that we've identified. So we've identified 4 different carbons that must be there based on the protons that we're seeing. But when you look at this thing, the spectrum, there's actually 5 carbons that are present. So there's 1 carbon that's missing. That is one that I'm going to mark over here as a kind of a piece that's very quiet in the proton NMR spectrum. It doesn't have any protons on it, so you're not seeing it. But there's certainly a piece there that is a C that must have 4 things attached, but none of them are protons. Okay. So when you get that bit, now you've got accounted for all the atoms in the molecule, the formula that you were given, you've got it. We can start putting this thing together. We know we have to have an OH, we know we have to have 2 methyl groups, and we know we have to have an ethyl. And you have to get all of those things connected in one molecule. If you're trying to connect them and you end up with a piece that you can't connect, it means you've got some kind of connectivity error. You got to get all the pieces connected together in the molecule. And one way you can do that is to make this molecule look like this. So I'm going to put the OH group here. I'm going to put, and I'm just hooking everything to this central carbon. And then, so the 2 methyl groups, identical methyl groups that we said needed to be there. And then we have this ethyl group that we need to put, and that goes in the 1 remaining spot. So CH2, CH3. And the reason I'm drawing it like I am is to just emphasize that there's a mirror plane of symmetry in this molecule that bisects it right down the middle like this, which is why the 2 methyl groups are the same as each other, and they give the same signal. It integrates to 6 because there's lots of protons that are represented by that signal, but it's one signal for all 6 protons. Okay, that's an example of one of these. When we come back, we'll meet, most of us are going to come to lab and meet in lab, and we'll work on lots of these. And then when we come back for lecture on Wednesday, we're going to do more of these to get just more practice. And eventually you're going to get good at this. You'll struggle for a while, I guarantee, but that's part of the learning process. The first few are going to be very slow, but then it'll get easier. So we'll check that out tomorrow. See you there.